Hello everyone, let's proceed with the lecture on the next topic. We are in topic 3, number systems part 2. So this is the outline of this week's lecture. We're going to cover generic number conversions, binary addition, subtraction, multiplication, division, sine magnitude, ones complement, twos complement, and then some arithmetic on the twos complement. Okay, so let's look at the general formula to convert a base 10 number into a base x. So as we have seen, if we have a base 10 number, we can use the repeated division method to convert to any base we want. And in the previous last week's lecture, we have seen that we can convert to hexadecimal, binary, and also octal numbers. But we can also have a non-standard base, for example, base 5, okay, or base 3, which is non-standard. So for example, hexadecimal is the standard base, which is base 16. So the way we do it is we can use a repeated division. So for example here, if we have a as base 10, so a here is base 10, and you want to convert this a base 10 into a base x, let's say for example base 5 or base 3. So previously we have seen that, for example, if you want to convert a here into binary, then your x here will be equals to 2. Okay, so if you want to convert into hex, decimal to hex, we divide by 16. So in this case, if you want to convert to base 5 or base 3, we make x equals to 5 or 3. And what we do is we do the division, we take the quotient and the remainder, and we do until we get a 0, okay, until 0 here, until 0 in the quotient. We can stop, and our solution will be from bottom up. So our solution will be Rn all the way until R0 base x, which is equivalent to a in decimal or base 10. Okay, what about the other way around? So given a base x number, how do we convert it into a base 10 number? So in this case, we can use quite similar to what we have seen last week. In general, we can say that we can use the summation of value to the power of the bit position. So for example here, if we have Rn all the way to R0 base x, we can convert to base 10 by multiplying the particular value at the particular bit position multiplied by the base to the power of the bit position plus, okay, all of the values in the bit position until R1, okay, which is the value in the first bit position multiplied by the base to the power of 1 plus the value at the 0th bit position multiplied by the base here it says to the power of 0. Okay, so using this formula we can convert any base, not necessarily the standard base, 2, 8 and 16. We can also convert to base 9, for example, or base 5, or even base 3. So let's have a look now at the 2-bit binary addition rules. So we have seen a little bit in the previous, in last week's lecture. If we do a binary summation of 2 bits, so for example here, if you do 0 plus 0, you will get a carry of 0 and a sum of 0. 0 plus 1 is equals to 1. The sum is equals to 1 with the carry 0. 1 plus 0 is also carry 0 with the sum 1. However, for 1 plus 1 in binary, the answer is 2. Okay, but the sum is actually 0 and the carry is 1. So let's look at example here of how we can do a simple binary addition. So it's quite similar to what we have seen all this while with the normal addition, where we have where you can put the binary numbers here. So 6 in decimal, this is the equivalent binary of 6, and this is the equivalent binary of 3, and we can just do standard canonical addition. Okay, so 0 plus 1 is 1. 1 plus 1 is 2. 2 is 1, 0, so we put 1 here and 0 here. And then 1 plus 1 is 2 as well, so we put 1 and 0. And then now this becomes 1, so 1 plus 0. Okay, 1 plus 0 plus 0, in fact. So 1 plus 0 plus 0 is actually 0, 1, or the sum is actually 1. So finally we get our sum is equals to 1001, which is equals to 9 in decimal. Let's look at the subtraction rule. So in the subtraction we have a minus b. So 1 bit subtraction. So a minus b, so 1 minus 0. We have the difference or the answer. Okay, the difference is 1. 1 minus 0 is 1, with a borrow of 0. Okay, where we don't need to make any borrow. 1 minus 1 is a 0 with also a 0 borrow. 0 minus 0 is a difference of 0 with a 0 borrow. However, 0 minus 1, which is supposed to be negative 1, okay, we'll have the answer as 1, 1. Okay, borrow as a 1 and the difference is a 1. Okay, so that's a little bit of the difference there. We'll look into more details later why a negative 1 is actually a 1, 1. Let's look at the example here for simple 5 minus 2 in binary. So if you have 5 here, so 5 is 0, 1, 0, 1, 5 in binary. And then a 2 is 0, 0, 1, 0 in binary. So we just do a standard canonical subtraction. So 1 minus 0 is equals to 1. 0 minus 1 is negative, so we need to borrow. So we're going to borrow from the other side here. So we minus here. And this now becomes 0. We put a 1 here. So 1 here, now here becomes 2. So here is in fact is a 1, 0. Okay, so 1, 0 in binary is 2. Okay, so when we put a 1 here, it's not a 1, but in fact it's actually a 2. So 2 minus 1 is 1, like this. And then we go to the next one. Since we have borrowed this one here, now this becomes 0. So 0 minus 0 is 0. 0 minus 0 is 0. And your answer is 0011, which is equivalent to 3 in decimal. Let's look at the binary multiplication. So in multiplication, we have 0 times 0 equals to 0, 0 times 1 equals to 0, 1 times 0 equals to 0, and 1 times 1 equals to 1. So this is quite straightforward in multiplication. And let's look at the a little bit more complex binary multiplication. So we're trying to do here, for example, 7 times 5. Okay, 7 times 5. So this is 7 in binary, 1, 1, 1, 1. Sorry, 1, 1, 1. And then a 5 in binary is 1, 0, 1. So what we do is we are going to multiply just like a canonical standard multiplication in decimal. So basically we are going to multiply 1, 1, 1 with this one to get this number. And then we're going to put 0 here. And we are going to multiply this 1, 1, 1 with this 0 here to get this number. Okay, so 1, 1, 1 multiplied by 0, we are going to get 0, 0, 0. And then we are going to drop 2 zeros down here, okay, just like a standard multiply. And we are going to multiply 1, 1, 1 with the final one at the MSB. Okay, so here is your MSB. Multiplied with the final one at the MSB, we are going to get 1, 1, 1. Okay, and then we can just add the three summations together. Add the three summations together. So 1 plus 0 plus 0 is 1. 1 plus 0 plus 0 is 1. 1 plus 0 plus 1 is... okay, so 1 plus 0 plus 1 is 2. 2 is actually 1, 0. So we're going to put 1, 0. Okay. Here is also 1 plus 0 plus 1 is actually 2, which is 1, 0. So we're going to put 1, 0. And here is also 1 plus 1 is 2, which is 1, 0. We're going to put 1, 0 like this. And finally, you can see in the standard binary, this is in fact 35 base 10, which is equivalent to 1, 0, 0, 0, 1, 1 base 2. Okay. So let's look at the division. So in division, it's also, you can use a canonical standard division form, where in this case we have the example is 31 divided by 5. So this is 31 in standard binary. Okay, base 10 standard binary. So 1, 1, 1, 1, 1 is 31 in decimal. and then we have the divisor here, it's called the dividend, and the divisor here is 5. So 101 is a 5. So 31 divided by 5. Okay, so 31 divided by 5. So what we do here is we can just do a standard. We put a 1 here. Okay, 1 here. So we put 101 down here. Okay, based on this number, and we do the subtraction. Okay, we do the subtraction. 1 minus 1 0. 1 minus 0 is 1. 1 minus 1 0. And then we are going to drop this 1 here. Drop this 1. We're going to put a 1 here. We're going to put 1 there, and we are going to get 101, and we're going to minus this together. We're going to get 0 0 0. We're going to drop a 1. Okay, we're going to drop a 1 here as our remainder. So our final solution here is in fact the quotient. Okay, the quotient is going to be 110, which is equal to 6, with a remainder of 1 in base 10. Okay, so we get the same answer there as how we do in decimal division. Okay, so that's it for this part of the video. So in the next part, we'll look at the sign numbers, how to represent negative numbers in binary format. Okay, so let's proceed with the sign numbers in digital logic. So in digital logic, we normally represent sign numbers using Sine Magnitude, 1's complement or 2's complement. So let's look at each one of it, how it works, and how we can analyze the concepts here. Okay, so let's look at the Sine Magnitude first. Okay, so in the Sine Magnitude, the leftmost bit is the sign bit, and the remaining bits are the magnitude bits. Okay, so as an example here, we are going to take the leftmost, or the MSB. We see here that the MSB, or the leftmost, is 0. So straight away we know if it's based on the sign magnitude, then the number will be a positive number. And what is the magnitude and what is the actual number? The actual number, we have to look, we take the remaining bits as a standard binary. So in this case is 25. And how we get 25 is basically, here is 2 to the power of, so here is a bit position 0, 1, 2, 3, 4, plus 2 to the power of 3, third bit position, and 2 to the power of 0. And that gives you 25, okay, in base 10, and it's positive 25. Okay, so let's look at the next example here. So next example here, we can see the MSB is actually bit 1. Is actually the value of the MSB is actually 1 in binary, which means that it's a negative number. And it's a negative number. What is the magnitude, or what is the actual value of the number? We look at the remaining bits, and we treat the remaining bits as a standard binary. And similar to the previous example up here, we see that it's actually the magnitude is 25, but we have the MSB equals to 1. Therefore, this number, if we say we are representing this binary in Sine Magnitude, then this binary is actually negative 25. Let's look at some more examples here on the Sine Magnitude. So given the binary here, okay, given these two binaries, find the equivalent find the equivalent the number in decimal using the Sine Magnitude format. Okay, so in the Sine Magnitude format, we see, so remember we take the MSB first, so the MSB is 0, so we know it's a positive number, and then we look at the remaining bits as a standard binary. So here is 2 to the power of 6, and here is 2 to the power of 2 as a bit position. So this is 68, so the answer is positive 68. So let's look at the next one. So the next one, we see that the MSB here is 1, so we straight away we know that it's a negative number. And the magnitude, we are going to look at the remaining bits as a standard binary, and the remaining bits is 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 1 plus 2 to the power of 0. Okay, so these are 4 digits there. And we calculate 2 to the power of 5 plus 2 to the power of 4 and so on, and we get the magnitude, and we just put a negative sign in the front because our MSB is logic 1. Okay, so we can also do the other way around. So given decimal number base 10, okay, given the decimal number base 10, can we derive or find the equivalent sine magnitude binary? Okay, so how do we find it? First of all, we need to know how many bits. For example, here we say, let's say this is 8 bits. So represent the decimal number 61 in sine magnitude using 8 bits. Okay, so we see that it's a positive number. So positive number, therefore, your MSB should be 0. And then your remaining bits should sum up to 61, as in this case. So 61 is a combination of 2 to the power 5, 4, 3, 1, and 0, represented by these bits, and this becomes plus 61 base 10. Negative 116. So negative 116 is a negative number. Therefore, straight away we give a 1 on the MSB for the 8-bit, and for the remaining bit should sum up to 116. Okay, which is 2 to the power 6 plus 2 to the power 5 plus 2 to the power 4 and plus 2 to the power 2. Okay, so that's sine magnitude. There are some issues with sine magnitude and also 1's complement. We'll see more about that one later. But let's try to understand what it means by the 1's complement. So in 1's complement, the negative numbers are the complement of the positive numbers and vice versa. Okay, so for example here, given this binary, okay, in 1's complement, okay, so given the binary here in 1's complement, we already know that if it's so if it's a 0, it starts with a 0 in the front, then we already know that it's a positive number, so it's plus 25. However, for negative 25, what we need to do is we need to get the plus 25 first. So this is our plus 25, and we are going to complement every bit in the binary. Okay, so for example, if it's 0 here, we're going to make a 1, a 0 here is a 1, a 0 here is a 1 here now becomes a 0. A 1 here becomes a 0 becomes a 1, a 0 becomes a 1, and a 1 becomes a 0. And after we flip all the bits, then that final representation there is actually our negative 25 representation in 1's complement. Let's look at a few more examples here on the 1's complement. So given an 8-bit or a 1-byte number 11001110, and we say that we are representing this byte in 1's complement. So how to find its equivalent decimal? So what we do here, we see here that is a 1 in the MSB, so we know it's a negative number. Okay, so that's the first one. So we know it's going to be a negative number. So but what is the magnitude? We know it's a negative number. What is the actual number? So what we need to do is we need to take the binary, and we are going to flip every bit in 1's complement. So we are going to flip, so this one here becomes 0, this one here becomes 0, and so on. Okay, and we are going to see what is the magnitude of the whole number. Okay, so here we see that this is 2 to the power 0, 2 to the power 4, 2 to the power 5. So if we sum up 2 to the power 5 plus 2 to the power 4 plus 2 to the power 0, we are going to get 49 in decimal. Therefore, this number that we have converted now becomes negative 49 in base 10. Okay, let's see a little bit more example here on the 1's complement. So find the equivalent decimal of the 1's complement binary. So here we have a 0 here means it's a positive, and here we have a 1 here is a negative. Okay, that one we know, but what is the value? So in the positive is quite simple. So in the positive we just calculate straight away. Okay, our 2 to the power 5, 3, 2, and 0, we get 45. But in the negative, it's a little bit tricky. Okay, in the negative, we are going to invert or flip every bit. So this one here becomes 0, this one here becomes 0, and so on. Okay, so here 1 0 1 0. Okay, so 1 0 1 0. We're going to flip every bit, and we are going to find what is the value, okay, in standard binary, okay, after we have done the flip. So here is 2 to the power of 3 and then 2 to the power of 1, and the sum is actually 10, okay, and therefore this whole number here is actually negative 10 in decimal, okay, using the ones complement. So we can also do the same thing. We can also do the same thing given the decimal number 132. So 132 is a positive number, so we can use a standard binary 2 to the power of 7 plus 2 to the power of 2, we get 132, and we can get simply the standard binary for 132. However, for negative 84, we need to find the magnitude of 84 first, okay, which is here. So the magnitude of 84 is 2 to the power of 6 plus 2 to the power of 4 plus 2 to the power of 2. In standard binary is given here, and then we need to flip every bit. Okay, so here we can see we do a flip. Okay, every bit flip 1010 1011, and therefore this whole binary here is actually your negative 84. Okay, so let's move on to the 2's complement. So 2's complement is probably the most important one. It's the most practical, mostly used is actually the 2's complement. Okay, 2's complement is the most important one, and how it works is basically it's taking the 1's complement and then plus 1. So let's have a look. So for a positive number is no issue. Okay, so for a positive number we can get directly is 25, but how to get negative 25 in 2's complement? So what we need to do is we need to take the 1's complement first by flipping every bit in the 25, and then we need to plus 1. Okay, so we plus 1 and get the 2's complement. So we can see here this whole thing plus 1. Okay, we are going to get a 1 there, and therefore it becomes negative 25. So remember that in 1's complement, negative 25 is given by this binary, and in 2's complement, negative 25 is given by this binary. So it's a different binary between 1 and 2's complement. Okay, let's have a look at more example here. So given 11001110, what is the equivalent, what is the 2's complement number in decimal? Okay, for this, so we know it's a negative number because a 1 here in the MSB, so we know it's a negative number, but what is the actual number? So what we do is we're going to take the flip, we're going to flip every bit, i.e. take the 1's complement, and then we are going to plus 1. Okay, so we see here that if we this one plus 1, we are going to get this binary, and from this binary we can get the equivalent decimal. Okay, using 2 to the power, just like what we saw in the previous slides. So we find that this particular binary is actually 50 in base 10, and therefore your original binary up here, okay, your original binary up here is actually negative 50 base 10. Okay, let's look at more examples here for the 2's complement, since it's the most important one. Okay, so here we see that it's a 0 in the MSB, so it's a positive number. So positive number should be quite straightforward. We can just calculate straight away our binary to decimal conversion. But here we have a negative number. So a negative number is a little bit tricky, where we remember we have to flip every bit and then plus 1. Okay, so here we straight away we flipping every bit plus 1, we are going to get a certain binary, and this is your magnitude of the negative number. Okay, so this is your magnitude of the negative number, which is simply negative 11. Similarly to the other way around, so 132 in base 10, we can convert, or we can represent, okay, 132 and also negative 84 into equivalent 2's complement binary. So in positive is quite straightforward. In positive, 0 in the front, MSB, and calculate 2 to the power of 7 plus 2 to the power of 2. However, for negative 84, it's a little bit tricky. We need to find the magnitude of 84. And then from here, we are going to get our solution by taking the flip plus 1. Okay, we're going to take the flip and plus 1, and here is your negative 84 in 2's complement representation. So some analysis here on the 2's complement. So what is the range of 2's complement? So we can see that a 0, okay, 8-bit, so 8-bit 2's complement, a 0 is actually a 0. And then a 1, a 2, and so on, and the maximum number is actually 127 for 8-bit. And the minimum number, or the smallest number that you can represent with the 8-bit 2's complement is actually negative 128, represented by this binary. Okay, so let's have a look at some examples here. So we can actually derive this and verify that how do you represent plus 19, negative 19 in sine magnitude, 1's complement, 2's complement. So we can see that actually in some cases it's the same. Okay, so for example in the positive, okay, this one, and this one, they're all the same, exactly the same. However, in the negative representation, they can be slightly different. As you can see in the sine magnitude, this is your representation, which is different than the 1's complement, and also different than the 2's complement representation. So it's very important to note that your binary, what number system are you using to represent the negative number. And here is an interesting part here, how to represent 0 in sine magnitude and 1's complement. So to represent 0 in sine magnitude, we can have a positive 0 or a negative 0. Okay, so so this one I will leave it to you to verify how to represent positive 0 and negative 0, and are they the same or not. And also in 1's complement, how to represent 0 in 1's complement. So this is another positive 0 and negative 0 case. Okay, however in 2's complement there is only 1 0. There is no positive 0 and negative 0 in the 2's complement. Okay, so let's finish up here with some arithmetic. So the arithmetic is quite straightforward, similar to a standard binary. Okay, this is an 8-bit addition. So for example, if you do 15 plus negative 6 in 2's complement, okay, so this is in 2's complement. So 15 is represented by this binary in 8-bit, and then negative 6, okay, this is the 2's complement, negative 6, and we can do a simple addition. So 1 0 1 1 1 is a 2, so 1 0, 1 plus 1 plus 0 is 2, and so on. And finally we are going to discard the carry. Okay, we're going to discard the carry, and finally we get the answer is 1 equals to 9. And let's look at another one, 125 plus 58. So 125 plus 58, what is the answer here? So we can see that we can put 125 here, and then we can put 58 here, and both are positive number. And we can do a standard addition. Okay, we can do a standard addition. We can do a standard addition here, and to arrive at our solution is 183. Subtraction also similar. Subtraction also similar, where we can represent 8 here and a 3 here. Okay, so 8 minus 3, 8 minus 3. So so 0 minus 1 is not possible. 0 minus 1 not possible. Okay, so we are going to borrow from here. Okay, we are going to borrow here. Now this becomes 0. This becomes 2. We're going to remove this, and this, now this becomes 1. This becomes 2. This becomes 1. And here is 2 minus 1. Okay, so here is actually 2. Okay, it's 1 0. So 2 minus 1 is 1. 1 minus 1 is 0. So remember, now this is 1. It's not 2 anymore because we transferred to the other side. And here is also 1 minus 0 is 1. 0 minus 0 is 0. And finally you get your 101, which is equals to 5. Okay, and we can also do 8 plus negative 3. Okay, so 8 plus negative 3, we can convert the negative 3 here. This is in 2's complement. 2's complement. So this is 2's complement, negative 3 in 8-bit. So we can do 8, this is 8, plus negative 3, okay, plus negative 3, and we can do a normal addition, and we discard the carry at the end there, and we're going to get the same answer, equals to 5. Okay, so just as a summary here, just a summary on the number system. So when given a byte, okay, given an 8-bit number, a byte 01010000, okay, it can mean a few different things depending on how you want to represent the bit. And as I mentioned, the computer only understands 0, 1 and 0 and 1s. Okay, and it's up to the user, it's up to us how we want to represent or what the actually the binary numbers mean. So for example here 010100 base 2, it could mean a 50 in hexadecimal, it could mean a 50 in BCD, it could mean 120 in octal, it could also mean 80 in decimal. In gray code we have the equivalent gray code. If you represent this byte as in ASCII, you can get a P character for ASCII. Okay, if you represent as a Sine Magnitude, okay, it might be different, it could be the same. We can also represent in 1's complement, 2's complement, again, it could be the same or it could be different. Okay, so I think that's it for this week's lecture, and I think we are done with the number systems. So in the next part, we are going to look into Boolean algebra and some logic gates.